Thank you very much. Thank you also for letting me invite a few students along with me today. So these are students who work really on the boundary between physics and engineering. They did physics degrees, but Jake is about to start his career off at BAE with a graduate scheme there. Ria and Thierry are both starting their third year of undergraduate at the University of Portsmouth and have been working this summer on building small satellites. So I thought this might be a wonderfully diverse group of engineers for them to meet today. So the title of this talk is Viewing the Universe with Massive Telescopes. The subtitle is 13.9 billion years in 13.9 minutes, plus or minus several mega years. I'll try not to keep you that long. Obviously, I can't tell you about the whole history of the universe in the time that I have today. But what I want to give you are essentially some of what I consider the highlights of astrophysics discovery to be. And in doing so, what I'm hoping to show is the role that technology has had and that essentially cutting edge engineering has had within astrophysics discovery. So I want to show you how that discovery has accelerated in the last 100 years. And the question for all of us will be, what will the next 100 years bring? So astrophysics itself is a really old science. It's the oldest science, and it began with our very first optics. So we've already seen a cat on the Zoom so far today. I don't think a Zoom is complete without seeing a cat. So here is another one. But our first optics were the eye. So with the naked eye, and in a dark site, you can see about 6,000 stars, and you can see 5 planets. So unsurprisingly, they have been known for tens of thousands of years. So the earliest signs are about 40,000 years ago in cave paintings of constellations on cave walls. However, despite the remarkable flexibility and complexity of our eye, of our natural lenses, they're limited both by their size and by their exposure time. So by exposure time, I mean, we can't ask our eye to gather all of the light for a minute and then look at the result in the way that we can do with a camera. So the fainter a thing is, the larger the light bucket you would ideally want to collect these photons arriving from an object. And so until technology developed larger lenses, the rate of astronomical discovery was really very limited. So in the 17th century, we did develop such technology. So we were able to make objects that appear larger and brighter using glass lenses. And very, very soon after these first telescopes were found, we discovered 2 other objects to our solar system. So Uranus and Neptune were discovered. The first type of telescope was called a refracting telescope. So in theory, we can polish bigger and bigger lenses, which would enable us to see deeper and deeper into the universe. But in practice, a bigger lens needs a much longer tube, and the tubes become too heavy to move and to keep stable. So the largest refracting telescope we have is in Wisconsin in the USA. It has a 1 meter diameter glass lens, and it needs to be 18 meters in length to be able to support that with the tube. It weighs 20 tons. So lenses were a wonderful invention, but they quickly reached sizes that were essentially no longer practical. And the rate of discovery in astrophysics again slowed until the next big technological breakthrough for astrophysics. And that was the mirror. So mirrors are great because they mean you can not only bend the light, but you can fold it. And telescopes with very large apertures no longer needed to be absolutely huge and really, really heavy. Telescopes can be more stable. They were no longer prone to kind of swaying in the wind or simply toppling over, as they had been in the past. And an equally important development in electronics in the 20th century allowed the moving and tracking of stars across the night sky. So this meant that we could take longer exposures of objects as well. And being able to add together all of this light that we receive from an object over several minutes enables us to collect more photons and to see much fainter objects. So these 2 breakthroughs together really enabled both the discovery of the remainder of our solar system, which you can see on the slide, but also something else that was quite remarkable. And that was the first galaxies. So the discovery of other galaxies actually only occurred in the 1920s. So for me, this has always been one of the things that I found fascinating about astrophysics. It's really only 3 generations ago that we believed that our own galaxy, so the Milky Way, our collection of billions of stars that we call home, was essentially our entire universe. And now 3 generations later, just last week, we're seeing images from some of the first galaxies that were ever formed within our universe more than 13 billion years ago. So that's a lot of progress within 100 years. And as we rapidly developed better mirror and camera technology, so our astrophysical horizons expanded exponentially. So this is an image I'm showing you now of Edwin Hubble observing in what was called the astronomer cage. So that's the place you would sit at the end of the telescope. And how you would take observations is you would sit there, observe with your eye, and draw what you see. And this is what the sky would have looked like at the time to a 1930s astronomer. Then in about 2000, we ushered in the beginning of what we would call the big data era in astrophysics. So this is our first digital sky survey. It's a 2.5 meter telescope. It's called the Sloan Digital Sky Survey Telescope, and it's at Kitt Peak in the US. And this telescope is still operating and still taking fantastic data. But nowadays, we regularly use much larger telescopes and can see the sky in much greater detail. So this is what we are now seeing on a regular basis. This is an image taken with a very large 8 meter diameter telescope. The picture that you're seeing are 8 meter telescopes. These are the very large telescopes in Chile. The little person in front is me. So you can see the size, the scale of these telescopes. And in the image, you can clearly see the richness of the universe as we observe it at the moment. So bigger is very definitely better so far in astrophysics, but large telescopes have particular challenges. So the biggest of these challenges for us are our gravity and our atmosphere. So how have new technologies helped us overcome these sorts of challenges? So gravity for us is a problem because as continuous mirrors of many meters, as we build mirrors that are much, much larger, these mirrors start to get very heavy and they can actually deform under their own weight. And they require unpractically strong and sturdy structures to surround them and to move them. So we have a couple of methods that we've used to respond to this particular sort of challenge. So the first I'm going to talk about is the use of sensitive actuators. So actuators being machines that convert energy into a mechanical force. And what you're seeing in the image are actuators that sit underneath the primary mirror of one of the VLTE telescopes. So modern telescopes now have very large arrays of these actuators attached at very small intervals to the underside of the mirrors. And the actuators have enough force and precision that they can deform the mirror, and they do so in such a way that they can keep the mirror really in a very perfect shape. So this helps in quite a number of ways, actually. This helps both to keep large mirrors from deforming under gravity. It helps to correct for the movement of the wave fronts that our atmosphere induces. And another use of the actuators is to protect the mirror and the telescope from ground movement. So I was at the Very Large Telescope in Chile when we experienced a magnitude 7 earthquake. And in the control room, at the moment an earthquake hits, everybody just jumps up and hugs a screen and desperately tries to not let things fall on the floor. But the thing that I found really astonishing taking data there is that through the combination of the system of actuators and a ring of clamps that are set around the diameter of the telescope, the outskirts of the telescope mirror, they were able to prevent any damage whatsoever to this 23-ton mirror. Within 3 hours, we were back on sky observing data again. And this system has actually withstood magnitude 8.8 magnitude earthquakes at the site. So another method that enables us to build incredibly large telescopes is interferometry. And this is essentially in astrophysics where we're splitting one massive telescope up into many smaller ones, which we link together. So to gain the highest spatial resolution, we want to have the largest diameter telescope. Large telescopes allow us to see finer detail due to the light's diffraction. So when the light hits an aperture, it tends to spread out. The smaller the aperture, the greater the spread. So small apertures cause an awful lot of blurriness to the object that you're seeing, and larger apertures cause less blurriness and allow greater detail. But to get this detail, we don't actually need a complete telescope. So a telescope with holes will produce an image with almost the same fine detail, but it won't be as bright. And so we use this method to build many smaller telescopes, and we link those up as if they were simply parts of one much larger telescope. The difficulty then really becomes a computational one. So the difficulty is, how do you make sure the data from all those different telescopes is perfectly in sync? That becomes the next challenge. And a remarkable recent measurement that was made in this way, using essentially the full diameter of the Earth as our telescope, was to measure the inner edges of a black hole for the very first time. And we've done this twice now. We did it again just earlier this year. And what we observed earlier this year was the inner edge of the supermassive black hole at the center of our own galaxy. The spatial resolution that was used to achieve an image like this one is the equivalent of being able to read the words on a coin from London if someone was holding up that coin in New York. So that's the level of spatial resolution that this has. So the second challenge for astrophysics is our own atmosphere. So the movement of the atmosphere blurs the light from the stars, making them beautiful, making them appear to twinkle. And our atmosphere also protects us from radiation, which is dangerous to us and only lets through small amounts of parts of the electromagnetic spectrum. So this may be wonderful for us, but this is a terrible thing. Both of these are terrible things for an astrophysicist. So how do we get around these awful challenges? So I'm going to talk about two things again. And the first one is, again, the use of those sensitive actuators. So this time we combine them with real-time laser measurements of the atmosphere itself. So we shine lasers up into the sky and we measure essentially what happens to that laser beam due to the movement of the air. And nowadays we can deform these mirrors so quickly and with such precision that we can essentially reverse the blurring that has occurred due to the consequence of air moving in the atmosphere. So this is a technique called adaptive or active optics. And it's an astrophysical technique that's also been being used now on Earth to look inside the human eye, to look in very fine detail and to identify things like macular degeneration and glaucoma. Two really remarkable astrophysics discoveries have been enabled by this technology. So they are the proof of the existence of supermassive black holes, black holes being regions of space so dense that no light can escape, and the direct imaging of other planets around other stars. So this is what I'm showing you on these two videos here. On the left-hand side is a video of 16 years worth of data, which is imaging the stars at the center of our own galaxy. These stars are orbiting an object that we can't see. Their motion, though, allows us to measure the mass of this invisible object. And the mass of that object turns out to be about 4 million times the mass of our own sun. So this is a huge object that they're orbiting. And that object is the supermassive black hole at the center of our galaxy. And on the right-hand side, what we're seeing is a direct image of extrasolar planets orbiting another star. So the bright light of the star in the center has been blocked out, but the little dots that you're looking at that orbit around that center are actually other worlds as they orbit their own sun. And with the recently launched James Webb Space Telescope, we'll actually be able to measure the atmospheres of distant worlds like these ones. So one of James Webb's key goals will be to search for essentially signatures of life in other atmospheres, looking for oxygen, looking for carbon. So the second way in which we can deal with the atmosphere is we can leave it. This is an expensive method. We can use planes, balloons, and satellites to get ourselves up high enough such that water vapor and atmospheric movement don't affect our results. So obviously going very far into space is the most ideal, but it's very expensive. And if your telescope breaks, you can't fix it. However, even an aircraft that's flying right at its limit can actually achieve very good results. So the bottom picture that I'm showing here is a telescope called the SOFIA telescope, and it actually lives aboard a modified 747, which is a wide and short 747, such that in this image it looks like it has an oversized tail. A 5 meter by 4 meter hole has been cut in the side of the aircraft, and there's a 2.5 meter mirror that's mounted there. So that's a mirror that's the same size essentially as the Hubble Space Telescope. I was actually lucky enough to take data on board this observatory. And SOFIA flies much higher than a regular jumbo jet. So commercial airlines fly between 28,000 and 38,000 feet. SOFIA operates usually around 45 to 46,000 feet. So this brings with it some unique challenges. It needs to get up there because it needs to get above the water vapor layers, which absorb the infrared radiation that it's trying to observe. However, at this height, the low air density basically results in less lift being generated for a given airspeed. So the airplane needs to fly faster if it doesn't want to stall. However, airplanes also have a maximum stall speed. So where the airflow over the ring is accelerated, and as that accelerates towards the speed of sound, it's going to form shocks, reducing the lift. The higher up in the atmosphere you get, the colder the air and the higher the altitude, you get the lower the sound speed. And this minimum and maximum airspeeds tend towards each other. So usually when you're flying in a commercial airline or a jumbo jet such as this one, you would expect a margin of error of 50 to 100 knots or so in speed. However, for SOFIA, the pilots only have a few knots between their minimum airspeed and their maximum airspeed before they would stall. So this really is precision flying. The other non-trivial thing about observing from an aircraft is trying to steady your instrument. So this is a time lapse of the instrument on board of the SOFIA aircraft. So you can see the large movements are when they go to different targets, but there also appears to be an awful lot of shaking. So actually, the pointing accuracy of this telescope is 0.5 arc seconds. It's better than seeing the width of a penny from 2.5 miles away. And while this looks like the telescope is bouncing up and down inside the plane, it's actually the telescope is perfectly balanced and the plane is bouncing up and down around it. So the pointing is stabilized using gyroscopes and thin layers of air and oil as lubrication around the system. So this is great, but I mentioned the best thing is to go deeper into space. So if we're going to go further into space, where should we go? What we need to find is a place which is has a stable orbit. 2 is not too far away so that we can easily communicate with our spacecraft. 3, we need to be able to power our spacecraft, so we don't want to be too far from the sun's radiation. But 4, our sensitive astrophysics instruments need to be protected from the sun, and they also need to be protected from the Earth and the Moon. So there are 5 stable points within the Sun-Earth system where we could potentially send a spacecraft and have it stay put. But there's actually only one of these that satisfies all of those 4 conditions. And in particular, the condition to shield the instruments from the sun, the Earth, and the Moon system. And so that is L2, Lagrange point 2. And so this is why we've sent things like the James Webb Space Telescope to L2. So I wanted to spend a few moments talking to you about the James Webb Space Telescope, since that is the most the recent telescope that's launched. It's one of the NASA Great Observatories, and it's just sent home its first pictures. So James Webb really was a feat of engineering unlike any other that we've had in astrophysics. So it has an extraordinary number of moving parts for a satellite. Now, usually you would try to minimize these as every moving part is essentially a part which can potentially go wrong. So we try and put up very simple spacecraft. But James Webb required, to achieve the size of the telescope, it had to be folded up. So the solar cells had to be folded, the solar shield had to be folded, and in fact, the mirror itself had to be folded up. So all of these got unfolded shortly after it was launched into space, and all appeared to be in good working order. So this image in the center is one of the first images sent back. And this is really remarkable. It's an incredibly deep image, the deepest image we currently have of the universe. The 6 bright diffraction spikes that you can see around the bright object in the field of view are due to the hexagonal shapes of the mirrors themselves. So the mirrors had to, in order to be able to fold them, they had to be made in segments to fit inside the rocket. And hexagonal segments were chosen. JWST has already set records for the oldest galaxies ever to be imaged. So some of the light that you're actually looking at that's captured inside this image has been taken more than 13 billion years to reach us. But we can actually do even better. So we can use the universe itself as a telescope on top of whatever telescope we're using. So mass bends light, and it can actually act as essentially like a large glass lens inside a telescope. So what you're seeing happen with these arcs that I've highlighted in this image, they're galaxies that are very, very far away. And the light from those galaxies, as on its travel towards us, is actually being bent around a much more massive object, the massive object being a galaxy cluster containing thousands of galaxies. And the light then is magnified and it's bent into these arc-like structures. So much like a regular telescope, this process enables us to essentially use the mass in the universe as a giant magnifying glass. It means we can see even further back. We gain greater magnification than we have engineered our telescope for. And in this way, we can use the James Webb Space Telescope to see all the way back to the first objects that form within our universe. So that was a quick tour of our last 13.9 billion years, and some of my favorite highlights from them. So the first light, we've seen the first light now that has escaped. We've seen the first stars that have formed. Those stars become galaxies. Some of those stars died, they became black holes, and we're observing with James Webb some of the first black holes in the universe. The galaxies merged and became more massive, and they end up where we are today, living inside our own Milky Way. So the vast majority of this knowledge has actually been uncovered in only 100 years due to the technological advancements of the time that we've been fortunate enough to live through. So today we can even hear the merging of supermassive black holes and detect how they impact space-time itself. So just as I finished this presentation, I wanted to let you all hear what it sounds like when 2 supermassive black holes merge. So those were the signals of the space-time that we live in actually shaking due to the mass of 2 supermassive black holes merging together. And we can actually detect this shake back here on Earth. So where will we go next then? We've had all this wonderful discovery within the last 100 years. So we're launching bigger telescopes into space. We're sending them further away. We are building ground-based telescopes with apertures now of up to about 40 meters in size. The UK is leading an enormous array of radio telescopes, which are going to come online within the next years. And these are going to generate more data within a day than the entire internet. So there are going to be data challenges ahead of us, as you can imagine, not just with how to analyze this data, but even with how to store this data. So for astrophysics so far, the story of the last 100 years really is bigger is better. But I want to leave us with one more thought. Is bigger really better? Our telescopes now don't need to be physically connected. Perhaps small and plentiful will begin to have a much greater role over the next coming decades, and in fact, bring this astrophysics discovery to more people. So what I hope I've shown you today is that astrophysics is both the oldest science, but it's actually a very young science that is experiencing an awful lot of change. And that rapid change in worldview is due to the new technologies that we've been able to have. And I'm looking forward to where that technology might take us next. Thank you.